I would like to introduce tonight's speaker. I am very, very excited about this talk because I heard about this talk because our speaker a little bit more than a year ago gave something like this talk to the Academy of Sciences in San Francisco. That's how I found out about it. And I heard good things about the talk, by the way. So no pressure. Okay. Rob Jedicke has had professional careers in particle physics, which means he's really smart, by the way, astronomy, and software engineering. By the way, he is our first football player to ever have as a speaker in our society. He was drafted in 1985 at the top of the third round by the Canadian Football League's British Columbia Lions in Vancouver, Canada, but sadly was cut, or maybe not so sadly, was cut early in the tryouts and went on to obtain his PhD in experimental particle physics from the University of Toronto. By the way, if anybody has ever seen Canadian rules football, it's much crazier than I used to watch it when I was a kid. I was going, incredibly violent. I'm glad you didn't do it because your body would have suffered and then you couldn't do science. He then held postdoctoral positions at the Fermi National Accelerator Labs in Batavia. So he was one of the Batavia boys. And then he went to University of Arizona's Lunar and Planetary Laboratory, which, by the way, is where next month's speaker is from, Sarah Moran. This is parenthetical. Next month, we're also having a very exciting talk by Dr. Sarah Moran from the LPL, who is using the James Webb Space Telescope to observe planets both in the solar system and outside the solar system. And one of the really exciting things is we've just recently discovered a planet that has, where's my wife? Would anybody know the name of the gas they've discovered? It's only on the Earth. What is it? It's something like that, and it's only generated by, on the Earth's atmosphere, it's only generated by phytoplankton, which is a very, very exciting possibility that there's something like phytoplankton in the, it's an ocean planet. Rebecca, what's the name of the gas on the James Webb Space Telescope planet that they've discovered that only is generated? Oh, she doesn't know. Okay. Anyway, but I digress. Anyway, so it's a very exciting talk. We're going to have her talk about this, and we're living in extremely exciting times. But back to Rob. Sorry, Rob, did I do that to you? Thank you. Sulfur dioxide. Okay. Let's see where I am here. Rob then spent more than 5 years developing image analysis software for surface interferometers at WICO/VICO Corporation in Tucson, Arizona. And then he's been at the University of Hawaii's Institute for Astronomy for the last 20 years. And there he's working on Pan-STARRS, which is a telescope that many of us know about, where he's managed the development of the moving object processing system. That's really quite amazing right there. You guys have discovered a lot of objects with that scope. That is one of the world's leading discovery systems for asteroids and comets. By the way, it's on Maui. I forgot to mention that. Rob lives in Hawaii, of course. By the way, his charming and lovely wife is a tour guide for Rick Steves and speaks fluent Italian. And I hope she's watching this right now because I'm dying to meet her. So let's see, what else, where am I here? And his current research interests include studying the properties of interstellar objects and developing plans to extract water from asteroids to provide fuel for spacecraft missions. So without any further embarrassment or to-do, our tonight's speaker, Rob Jedicke. Go ahead, Rob.
I think I'm going to try and use the lavalier. Does this work? Yeah, I think this works well, right? Yeah.
Get the what? My
Okay.
stick. Yes, thank you.
I think we've got some technical issues to deal with here.
Yeah, my wife uses it to beat me. Here we go.
Give me a second here. You got it? All right. Okay, well, thank you for that. Yeah. Thank you for that introduction. Very generous of you. I appreciate the opportunity to be here. Never been at the Science Center before, so I got one here. And tonight I'm going to be talking about the peril and profit of near-Earth objects. I'm from the Institute for Astronomy at the University of Hawaii. And first I'm going to start off with the peril. near Earth objects, okay? Before we get onto the profit aspect of it. But even before that, as it was mentioned in the introduction, I played football. And most people would think, why am I showing a football picture at the beginning of astronomy talk? Well, these images there are of me. Now, of course, they're black and white because they're from 45 years ago. But even though it was a long time ago that I played football, I still like to get my performances started off with a bit of a cheer. So I need you to help me start my talk off, okay? So
what position did you play?
Americans always ask me that question, and most people think I played tight end. But in Canada at the time, 45 years ago, I was one of the biggest guys on the team. So I was actually an offensive lineman. Yeah, I was a bit bigger at that time as well. But in Canada, it was everybody's smaller in Canada. So you know how this works. I yell out something, you yell it back to me, okay? And that will be a cheer that gets me going with my talk, all right? So okay, so this is very embarrassing for me. So you got to help me out here. So give me an I, give me an M. Give me a P, give me an A, give me a C, give me a T. What do you get? Now we don't have any sound. We don't have any sound. All right. So this is, of course, asteroid impact from a movie. Probably most of you have seen it, I'm guessing, at some point. Maybe you don't remember it. And without the sound, it lacks some of its impressiveness. So, yeah. But you definitely don't want to be clueless like this gentleman right here when a tidal wave is coming at you. Right? Anyhow, so most of you, I imagine, recognize that movie clip from the movie Deep Impact. I was a consultant on the movie, although there were many, many consultants on the movie, and my name didn't even make it onto the credits at the very end. But it still felt really great to have one of Steven Spielberg's writers come, and he met me at Kitt Peak when I was working at Spacewatch, and he spent about 6 hours with me. I let him move the telescope around. I let him find asteroids, told him everything I know about asteroids, gave him ideas for things. And I had a really great time. And for that, I actually got invited to go to some red carpet premieres of movies. I got to see Amistad when it showed up in Hollywood. That was great. Yeah.
I was talking to Peril, and because Gene and Peril were also.
Yeah, they probably were on the credits. Yeah. Well, so Deep Impact, all the people in my field just loved the movie Deep Impact because it was pretty accurate. I mean, it was pretty good at the time for illustrating what we thought about asteroid impacts. But in fact, I honestly didn't like the movie very much. If you're going to watch a movie, if you haven't seen it yet, watch Armageddon. Armageddon is a lot more fun to watch, and it's what I want to see when I watch a movie. It's just lots of excitement, things blowing up. Completely bad science, but it's a lot of fun to watch. So Deep Impact, the movie. Steven Spielberg was, of course, the director or producer. I always get them confused, and there's me. And I always like to compare the Deep Impact incomes, because I tried to estimate how much money Steven Spielberg probably made on that movie. And I estimate that based on the sales and all that, he probably made something like $10 million on the movie. And for all the work that I did, spending 6 hours with his writer, giving him all the ideas, he actually sent me a check for $100. So if you've got children or grandchildren, or maybe you're actually considering going into the field yourself, you might want to look at how many zeros are there before you decide to enter academia rather than the movie industry. So first of all, I'm going to start off telling you about what asteroids and comets are. And asteroids, so I know that you said next month you're going to have a speaker from the University of Arizona who's going to be talking about images with JWST. And people who do things other than asteroids have a really big advantage, because all asteroids look like potatoes, right? So it's I can show you so many pictures of asteroids and they all look like potatoes, and you can get really good at identifying this potato relative to the other potato. They're just not really exciting to look at. But JWST images of the planets, of galaxies, planetary nebulae are just fantastic. Anyhow, this is an asteroid, okay, and this is a comet, and I like to show these two images together because it illustrates the fact that there isn't really that much difference between them. I think you'd probably have to be an expert to really distinguish between them. And in fact, they had to do some real fine image processing just to be able to see a jet of material coming out of this comet right here. Right? So most people think about comets as being really bright in the sky, really big, jutting off all this gas and dust and ice and water. But in fact, if you get right down into it and you look at them, they're really kind of hard to tell apart. Maybe this has got more smooth parts on it. It's got maybe some more sharp edges, but really they look very similar. So, and in fact, I personally in the field, I don't like to make a big distinction between asteroids and comets, although lots of people do. Lots of people have made their whole careers on the differences between asteroids and comets. I like to look at them as being very similar. So I consider comets to be dirty ice balls, and I consider asteroids to be icy dirt balls. Okay, and they're on a spectrum, right? They're a spectrum. So many asteroids have water in them. Some have lots of water in them, and some comets have very little water in them, right? So there's a real spectrum there, and and deciding which is one and which is the other is not easy. In fact, there is no really precise definition of it. People call comets things that show activity and asteroids things that don't show activity. But the amount of activity we see depends upon how good the telescopes are, how sensitive your instruments are. So it's not really a scientific metric that we use to decide between the two. The third thing that I want to talk about is meteors. Meteors are chunks of asteroids or comets that enter into the Earth's atmosphere. This is a famous one called the Peekskill meteor, which occurred over the northeastern United States. It was probably about the size of a Volkswagen car when it entered the atmosphere. It broke up into many different pieces. I know you're seeing all these different chunks coming in. It was probably about as bright as the moon when it hit. And then it traveled through the atmosphere and eventually came down a place called Peekskill, New York. And a chunk of it, not the entire thing, but a baseball-sized chunk of it landed on this corner of this car and made the car very valuable. The car was only worth $100. It was only worth about $100 before it got hit. After it got hit, it was worth many thousands of dollars. So a meteor is a chunk of an asteroid or comet that comes through the atmosphere. And then when it hits the ground or a car, it's called a meteorite. And a meteorite can do damage to a car, can do damage to houses, can do damage to things. But a very big meteorite can do damage to the entire global climate and humanity. So what do asteroids look like? Like I said, they look like potatoes. Here's another asteroid. This is an asteroid Ida. I like to give people an idea of scale typically when I show slides. And this means a little bit more if you're from Hawaii. But if you've been to Hawaii, this is the whole island of Oahu. Okay. Now, Ida is an asteroid in the main belt of asteroids, which I'll be talking about shortly. Oahu is the island that I live on. Honolulu is down here. I live over here. And the whole island of Oahu is about 30 miles across in its long axis, as is Ida, right? So asteroids can be big. Asteroids can be as big as islands. Asteroids can be as big as continents. But the small ones that you see, the meteors that are going through our atmosphere, they're typically the size of peas. Most of the time when you see a meteor in the sky, you have to be bigger than that to see it from San Francisco, probably. But if you're out in the desert in Arizona, you can see pea-sized meteors passing through our atmosphere. And when you see the pea-sized meteor, they're typically about 60 miles above you. So you're seeing a pea-sized object 60 miles above you. And you're seeing it only because it is moving so fast. Typically, they're moving at about 10 or 15 miles per second. That's about 20 times faster than the speed of a high-speed rifle bullet, right? And they're coming in so fast, these little pea-sized things, that they burn up due to friction with the Earth's atmosphere. And even though they're 60 miles away, you can see them. So that's just a pea-sized thing. So just imagine what would happen to you get a car, or you get something the size of a building coming in the atmosphere. That can do a lot of damage to the Earth. So let's review where the asteroids and comets are. Is there any way to turn down these lights here? Good. It'd be best if you could just turn the ones down the front, but if you have to turn them all down, that's okay. So, that's not bad, yeah. So here is a schematic representation of the solar system that actually represents real asteroids and planets. But we got the sun here in the center, and then Mercury, Venus, the Earth, Mars, and I think at some point you'll see Jupiter coming around the corner here. And all the planets, of course, if you're looking down on the solar system from the north, they're all going counterclockwise around the sun. All those little green dots out there, they represent main belt asteroids. There's about 1 million asteroids in the main belt of asteroids that are larger than about 1/2 a mile in diameter. 1 million larger than 1/2 a mile in diameter. But they're out there sort of safely between the orbits of Mars and Jupiter. They have been out there for 4.5 billion years. Most of them have stayed out there. Most of them are going to continue to stay out there. They're never, ever going to venture into the inner solar system. But some of these yellow and red dots you see here are asteroids that have ventured into our inner solar system. And those are called near-Earth objects, or NEOs for short. So that the NEOs are objects that are badly named, okay? Just because they're near-Earth objects doesn't mean they actually, some of them never come near the Earth, okay? We just call them near-Earth objects. But some of them can come near Earth, and that's how they get their name. But in fact, the technical definition of a near-Earth object is only that it is an asteroid or a comet that can approach to within 1.3 astronomical units of the sun. 1 astronomical unit is the distance between the sun and the Earth. So 1.3 just means 30% larger distance from the sun than the Earth goes around the sun. But of course, it's a complete sphere around the sun. It's a sphere with a radius of 1.3 astronomical units. So any asteroid or comet that approaches within that sphere is called a near-Earth object. Yeah.
Rob, that's a very arbitrary choice. I assume there's some well thought out reason behind that.
I wish I could tell you that you were right. It's actually pretty arbitrary. There's really no good reason for it.
Yeah, one would think I would have chosen anything besides Mars.
Yeah, there's really no, if you look at the distribution of asteroids in our solar system, nothing happens at 1.3 AU. There's something that's a little bit better. It's called the minimum orbital intersection distance. And so we have another definition, a subclass of asteroids called potentially hazardous objects. And the potentially hazardous objects are defined by coming within 0.05 5% of an astronomical unit to the Earth. And that actually has, I used to think it was arbitrary, but it actually turns out to have, you can actually sort of justify it. But when it was originally quoted as that number, it was sort of like a back of the envelope calculation, and the back of the envelope calculation actually turned out to be pretty good. So it actually has a good reason. Anyhow, I should move on. Yeah, no worries. So the asteroids, those near-Earth objects have hit Earth in the past. Some of them with tremendous destructive, tremendous damage to the surface of the Earth. This is a map of impact locations across the surface of the Earth. And if you look at it, it looks like the asteroids really hate North America, Australia, and Europe, and are quite favorable to Russia and Africa. But in fact, that's just a selection effect, right? That it's been difficult to do asteroid or impact research in Russia because of geopolitical reasons. In Africa and South America, jungles make it difficult to detect the evidence for impact craters. But Australia and Canada, the Canadian Shield, are really great areas to preserve the effects of asteroid impacts. But the idea is that asteroid impacts have occurred in the past over the entire surface of the Earth, some of them catastrophic for humanity or for life at the time. And in fact, one of the most famous ones is this one right here at the what is now the northern coast of the Yucatan Peninsula in Mexico. And that is famous. At that time, 65 million years ago, there was an asteroid that impacted the Earth that was 6 miles in diameter, okay? 6 miles in diameter, and it was moving 20 times faster than the muzzle velocity of a bullet coming out of a high-speed rifle. So something 6 miles in diameter moving 20 times faster than a bullet, and it struck the surface of the Earth off the coast of what is now Yucatan Peninsula at that speed, and it wiped out 80% of all life on the planet at the time. Everything on the planet burned. There's a layer of soot around the entire surface of the Earth that corresponds to every single thing on the planet burning at that time. There's evidence for tsunamis in North Dakota, right, where they have 10 meters, like, a layer of rock and dirt that was deposited due to a tidal wave way up in North Dakota. So this had tremendous effects over the entire planet, wiped out 80% of people. In fact, it it was proposed that it was the cause for the demise of the dinosaurs. Now, this is I think this simulation is really fascinating. This is a simulation, computer simulation of what happened when that 6-mile diameter impactor hit the Earth at 20 miles per second. And it'll play over and over again, but basically the Earth creates a bowl, the impact causes creates a bowl, the Earth's surface then sort of rebounds and it sends up that sort of mountain, the mountain then collapses back down, and you get this very distinctive concentric crater. This is a system. Anytime you've got a large enough impactor, you create this concentric crater system. You can see these on the moon. There's many examples on the Earth as well. But the really incredible thing here is how big this was. This is a schematic representation of Mauna Loa. Mauna Loa is the tallest in Hawaii. Mauna Loa is the tallest mountain in the world measured from the base of the ocean floor. It is something like 10 miles high, right? So this is Mauna Loa, 10 miles high. So imagine how high this mountain was. Okay, this is a 20-mile high mountain that formed when that 6-mile diameter object hit the Earth 65 million years ago. Now, if that doesn't get your interest already, the time scale of this whole process is about 20 minutes. So in 10 minutes, this 20-mile high mountain was formed. Sorry, in 10 minutes, the 20-mile high mountain was formed, and then it collapsed back down in another 10 minutes. So this whole process took place in 20 minutes. There were massive earthquakes over the entire Earth. There were meteors falling down all over the Earth. And it was the meteors, the radiant energy from those meteors falling all over the Earth that raised the temperature of the surface of the Earth to about 400 degrees Fahrenheit. So this is the kind of thing that we want to avoid happening, the peril of asteroids hitting the Earth. So there is now no doubt about it. An asteroid killed the dinosaurs. There was quite a controversial idea at the time when it came out in the mid-80s. We were just having a discussion today about this, that it was proposed in the mid-80s by a guy named Walter Alvarez. And at the time it came out, he took a lot of vitriol. He took a lot of, there was a lot of animosity towards him for proposing that asteroids and that asteroid impact wiped out the dinosaurs, because at the time people thought that it was these Deccan volcanic traps in India, or maybe it was just predation or starvation or some other reasons. But anyhow, I think it's right now, it's quite well established that an asteroid killed the dinosaurs 65 million years ago, and it was that specific one that hit off the coast of what is now the Yucatan Peninsula. So how do we reduce the impact risk? We are smarter than dinosaurs, so we should be able to reduce the impact risk. And we do it using telescopes. We find asteroids. I went to the University of Hawaii's Institute for Astronomy to help them build this telescope, the Pan-STARRS telescope, which is on Haleakala on the island of Maui. And there's a new telescope that is being constructed right now in Chile called the Vera Rubin Observatory. It is currently planned to be operational in about 2 years. And it is a really phenomenal system. It's got a gigantic mirror that's more than 8 meters in diameter. And it is going to be able to image, I think it can image the entire sky, visible night sky, every 3 or 4 nights. And it can go down to, if you know the magnitude system, it can go down to a magnitude 23.5 or magnitude 24. So, and it is planned to do this continuously for 10 years. They think, because I'm more interested in asteroids and comets, they think that it will be able to detect 10 times more asteroids and comets than we currently know. So how do we find the asteroids with these systems? Well, what we do is we take a variety of images. We take a set of images. We come and we take one image at one time a night. And this is how people have actually been finding asteroids for a long time. I'm sure Gerald just won the award, so I'm sure he knows all about these things. But this is how it's been done for 100 years, finding asteroids. People would take an image of the sky at some time. In this particular case, I say it's at midnight. They come back, say, a half hour later, and it depends on the exact timing, depends on a whole bunch of factors, but half an hour is sort of a typical time. And then we come back even another half hour later, take another image of exactly the same location. Now you see, if you can recognize, most of it would probably recognize the galaxies here. I think there's a few other galaxies in there somewhere. Many of these things here that you see here are stars. And then what we do is we superposition these things on top, these images on top of one another. And then we do something where we just sort of rapidly go between them. And it used to be just before I got into the field, David and I were talking about the shoemakers. The shoemakers used to use some sort of a blinking technology where they would actually do these observations by eye. I'm quite thankful that I got into it when computers were around, and they developed computer algorithms to do this for us instead. So the computer algorithms now look for these things, but now I'm actually blinking between the three images in succession. And if there is an asteroid in the field of view, you'll see it move in a line between the three images. So here's the other galaxy that I was looking for earlier that I couldn't see. And if you're all looking carefully, I hope that you found these two asteroids that are right there, right, that are moving, one in the lower left, one in the upper right. Right, so those are asteroids in this field, and that's how we find asteroids, and it's still being done that way. It's just being done quickly with computers now. Memories of Clyde Taubman, yeah. So what do we do if we find one? That's the next question. Okay, so we've been trying to find asteroids that might hit the Earth someday, and but the question is, what if we do find one? There's certainly asteroids out there. There are certainly asteroids out there that have our name on it. And we just hope that we can find them before they find us. So what if we do find one that is going to hit us in, say, the next century or so? Well, I like this figure right here, because what you want to do, right, is like we found this asteroid that's got the Earth in its target, right? The Earth is targeted, right? So what we want to do is we want to go and we want to sort of nudge that asteroid. We want to nudge that asteroid so that it no longer is targeting the Earth. But what if we don't nudge it right? Right? What if we give it a nudge, and now instead of it hitting Washington, D.C., it's going to hit Moscow, right? That would not be good. When we nudge it, right, we want to make sure that we nudge it so that its target is nowhere near the Earth, right? We have to be very careful. We have to design systems that are effective at deflecting the asteroids from the Earth. So we want to deflect the asteroid, but how do we test the deflection? Well, some of you probably have heard about the DART mission that's been out, that has just completed, but in fact, it completed about almost exactly a year ago, the double asteroid redirection test. Is all this stuff on your system, or is this on mine? It's your system, okay. So, so the double asteroid redirection test was a NASA mission that went to try and test our ability to deflect an asteroid, right? If we find an asteroid that's going to be hitting the Earth, we want to be able to test the deflection. But it turns out that trying to deflect an asteroid that's half a mile in diameter would be really difficult with a little spacecraft that's the size of a car. And you know, you're slamming into, it's like, you know, a little fly slamming into a big convoy truck, right? The fly is not going to deflect the convoy truck. And if you have even the most massive spacecraft that we can create right now, and you slam it into a half-mile diameter asteroid, it's going to be really difficult to measure the impact or the change in the asteroid's motion. So instead, they came up with this clever idea. What they do is they have what's called a double asteroid system, where you've got a big asteroid here that's sort of half a mile in diameter, but you've got another asteroid here that's about 200 yards in diameter. And it turns out that and this 200-yard diameter asteroid is in orbit around the big asteroid. And it turns out that if you slam a spacecraft that's the size of a sort of a small car into the smaller asteroid, then what you can do is you can change the period of revolution of that asteroid around the bigger asteroid. You can change it. So it used to be 6 hours, and we can change it to 6 hours and 10 minutes. And that by measuring how much we changed the period of revolution of that asteroid around the big asteroid, we can actually determine how effective our deflection system is. So the asteroid that is the primary asteroid, the big one that's half a mile in diameter, is called Didymos, and the asteroid that they slammed into is called Dimorphos. Dimorphos, like I said, is about 200 yards in diameter. So think about it as sort of like twice the size of an American football field. Canadian football fields are much bigger. And so they slammed a spacecraft into this 200-yard diameter asteroid. So this is animation. This is not a real movie of it. This is an animation of that spacecraft slamming into it. It passes the asteroid Didymos, and then it slams into the surface of Dimorphos. And now you get an idea of the scale of the spacecraft relative to the scale at Didymos. And Didymos is, you know, like I said, 200 yards in diameter. One thing I want to point out So this is all just a simulation, but even in the simulations, they have this 45-degree cone here. And this is, I think, really interesting because it looks kind of artificial, right? That, why would it all come off at a 45-degree angle? But this is actually something that's been observed in laboratory experiments for a long period of time. And in fact, a lot of people just assume when a crater gets formed that the ejecta comes off at a 45-degree angle, just because it's a nice simplifying assumption. But this simulation assumes that, but I'm going to show you in a little bit that it actually seems to be real. So I don't think I can actually show this because we don't have the sound here. I'll skip over that one. So here's something going on. So this now is actual real imagery turned into a sort of a GIF movie from the DART mission as it's approaching the asteroid Dimorphos. So you're going to see the asteroid, this is the big one, the Didymos, right? This is Dimorphos that it's going to hit. So the spacecraft is coming in, it's taking an image every periodically, it's doing some course adjustments, and you're going to see it pass by. It's going to fly by Dimorphos. It's moving at about 4 miles per second, and this asteroid here is only half a mile in diameter, right? So it's moving at 4 miles per second, and it's going to slam into this little 200-yard diameter asteroid at 4 miles per second. And look at the shape of the surface here. You can see the surface is just covered in these rocks, and it turns out that that's a common feature of the surface of these kind of size of asteroids now. And you might wonder, why am I showing you a screen where there's only an image at the top and all red at the bottom? That's because this is the last data that got back before the spacecraft slammed into the surface, right? So this is the last bit of data before, the last bit of transmission that it could actually get. So at the same time that the NASA DART spacecraft was traveling towards the Dimorphos, it released a European Space Agency ESA spacecraft called Licia Cube, and it was basically a small spacecraft that followed behind the DART spacecraft to get an image of what would happen, or what happened to the asteroid after it was impacted. Unfortunately, it turns out that there was some optical problems with the ESA spacecraft, and I don't think that they've been able to correct it. So this is an image taken, or a movie taken by the Licia Cube ESA spacecraft coming in. So Didymos is, of course, the bigger object, so it's the brighter one, and Dimorphos is the smaller object, the fainter one. And now you're going to see a series of images taken by this little spacecraft coming into it. And this is after the impact already, so you can already see the material coming off of Dimorphos here. And then the spacecraft, the Licia Cube, passes by and then turns around and keeps imaging it, right? So you can see the material coming off of this Dimorphos asteroid here. Now, what I like about it is that when you look, I pulled off one frame here, and you can look at this, and that's also got that 45-degree angle there, right? So that the simulations and the stuff that we're seeing in the laboratory, and in fact, right now I'm doing some simulations about impactors hitting the moon, and I'm assuming that the ejecta comes off of the impacts of the moon at a 45-degree angle. And I like the fact that this actually shows that this happens in reality when something hits an asteroid. Now, there's one last set of images. This is taken by the Atlas spacecraft, Atlas telescope system. Atlas is a multi-telescope system that's run out of the Institute for Astronomy where I work. And they have telescopes on Haleakala, on Mauna Loa, in South Africa, and in Chile. I believe that these images were taken from the one on Mauna Loa, or maybe it was on Haleakala. But these are now a set of images. I think it's taken every few minutes by the Atlas Atlas telescope. And you can see what happens from the ground. So these are stars, okay? And the telescope is going to be tracking on the Didymos and Dimorphos system. Now, since it's on the ground and it's a relatively small telescope, you don't see the two asteroids separately here. They all look just like one big thing. Now we're tracking on the asteroids. So the stars are going to move through the field of view. So you can watch right now, the asteroid is moving, stars are moving behind it, and now it gets hit by the spacecraft, blows off a massive amount of dust, and creates this gigantic cloud that falls off, right? So even from Earth, you can see the results of an impact of just a tiny little spacecraft on an asteroid 100 million miles away. And you can see that it creates a tremendous amount of dust. So follow-up mission is going to be the ESA, the European Space Agency, is going to be sending a spacecraft called Hera in a few years. They're going to go back to exactly the same asteroid system, and they're going to look to see what actually happened, right? And so we want to measure how much did we change the period of revolution of the Dimorphos around Didymos. We want to see how big a crater we created. We want to measure the whole properties of the system, all because we want to characterize how effective we can be at deflecting asteroids from hitting the Earth. So why do we do all this? Why do we build telescope systems like Pan-STARRS, the Vera-Rubin Observatory, run missions like DART and Hera? It's all to save the planet. Okay, so this is all about reducing the peril to the planet of near-Earth objects. So moving on now to the profit of near-Earth objects. Okay, the asteroid mining. Okay, we think that there is a way to profit from near-Earth objects through asteroid mining. And for me, it's all about the money, right? Being an astronomer, I'm not going to say we're not well paid, but we're certainly not, software, Silicon Valley, software engineer type money. But I like to think that, the asteroids could actually open up a $1 trillion space economy, a $1 trillion industry for the 21st century. Now, this all sort of ties into a lot of things. So in the United States has passed a law called the U.S. Commercial Space Launch Competitiveness Act, which is really interesting because it actually opens up the market, the market for asteroid mining. It has been called the most sweeping legislative recognition of property rights in human history. Okay? The idea is that you cannot go and plant your flag on an asteroid and say, this is my asteroid. Okay, that's not legal according to the United States. But you can go to the asteroid and you can extract whatever you want from the asteroid, and then you can go sell that material to whoever you want or whoever will buy it. Okay, so the material that you extract from an asteroid is yours, but not the asteroid itself. And I think it's kind of a clever idea. Now, of course, I don't think any other countries have have agreed to this, right? So, what actually happens when people start doing the mining is a really interesting question, but you've got to start somewhere. So starting somewhere is probably not this. When I was a kid, this is when they were talking about asteroid mining, this is the kind of images that I remember seeing. And maybe you watch The Expanse and you see things like this. But in fact, this is pretty far in the future still. I like to believe that we can get there really quickly, but probably realistically, it's not going to be the first thing we're seeing. Instead, I work with a company called TransAstra that's based in Los Angeles. And it's been around for about 10 years. About 10 years ago, you may have heard there was a lot of hype about a lot of asteroid mining companies. TransAstra is maybe the only one or only a few that is still around, and it's actually thriving. It's doing really well. And its end goal is to eventually develop a space industry in asteroid mining. But of course, it's got lots of other steps to do along the way. And I hope to give you some idea of how we hope to achieve that here. So the market for the TransAstra was actually started. I was actually at this meeting about 10 or 12 years ago, where representative from United Launch Alliance. Anybody here work for United Launch Alliance? You never know in San Francisco when there's somebody here working for them. But United Launch Alliance it's a bona fide company. You may not have ever heard about it, but it's a billion dollar company with thousands of employees and hundreds of successful launches. It's really good at doing what it's doing. It launches spacecraft for the military, for NASA, for various other organizations. So it's a legitimate company. And there was a representative from this company that was at this meeting I was at, and they offered to pay $10,000 per liter of water. Okay, they were doing what maybe NASA should have done 40 years ago, right? And say, hey, we will actually pay you if you can get water into high Earth space. So that's the key, is that they'll pay $10,000 per liter of water, but not on the ground. Nobody's going to pay $10,000 for a bottle of water down here. That bottle of water has to be in high Earth orbit. And why are they willing to spend that much money for it in high Earth orbit? Well, because it would cost them $20,000 to get it to high Earth orbit. So if they can pay somebody else $10,000, they're actually doing well. And why is water important? Well, water is fuel. Water can be split up into hydrogen and oxygen, and that makes an excellent fuel. But you can also use the water as steam. You don't need to separate it into hydrogen and oxygen. You can just use it as, you can just heat it up really hot and create steam. So you can actually create steam-powered spacecraft, right? Which I think is really fascinating. That the steam engine opened up, North America and Europe and industrialization, and the steam engine may be coming back in space. Water, of course, can also be used for radiation shielding. It's easily shaped, and it's also a really good radiation shield. So if you've got a volume that you want to protect from radiation, you've got a thin shell of material that's empty, you can pump the water into it when it's liquid, let it freeze, and all of a sudden you've got a nice radiation shield that can be shaped in any shape that you want. Of course, water is also useful for human consumption and agriculture. And maybe the most important, the key factor, is that it's straightforward to mine. At least we think it's straightforward to mine relative to anything else that you can get. So another key is that water is everywhere. When I was a kid, 50 years ago, 55 years ago, I was reading every astronomy book I could in our library, and I don't remember reading about water being everywhere. I remember it all being sort of mysterious. Where's water? Are the polar caps on Mars? Are those water? What are they, right? But now we know that water is everywhere in the solar system. It's just really hard to get from most places, right? There's water on Mercury. I don't know about Venus. There's lots of water on Earth, lots of water on Mars, in the polar caps, below the, even really shallow under the surface of Mars, like inches under the surface. There's ice under the surface of Mars. There's lots of water in Jupiter, Saturn, Uranus, and Neptune. Of course, Saturn's rings are almost all ice. Right? If we could get there and get the ice, that'd be lots of water there, and on Pluto too, right? So water is everywhere. It's just hard to extract from most places. So where is it most easily accessible? Some kind of delay here. So one of the places that water might be accessible is the lunar poles. It turns out that at the north and south pole of the moon, there are pretty well established sources of water, of ice, not water. And it's really fascinating how the water gets there and where the water is located. It has to do with the fact that when the moon is rotating, Okay. Well, go to the next one. So when the moon rotates on its axis, it turns out that its axis is really perpendicular to its path around the sun. And so that means that if you've got a crater at the north or the south pole, the interior of those craters don't see sunlight. This is an image made, or a movie made out of a series of images, real images. This is not simulations, of one of the craters at one of the poles. And you can see that over the course of a month, which is how long it takes for the moon to go around the Earth, over the course of the month, light never reaches into the base of this crater here, right? And the base of these craters here, they can be some of the coldest places in our solar system. They're even colder than the surface of Pluto, because the surface of Pluto sees sunlight, even though it's 40 times further away than the Earth is from the sun. Pluto's surface sees sunlight. All of the surface sees sunlight. But these craters here have not seen sunlight in more than 1 billion years. They're some of the coldest places in the solar system. So how does water get in there? Well, there's still a lot of debate of exactly how the water gets in there and where the water formed. But the idea is that any water that does get to the surface of the moon, maybe a comet slams into the surface of the moon, or an asteroid slams to the surface of the moon. And as I said, asteroids and comets contain water. So now the water is on the surface of the moon, but it's not going to form lakes, right? It's not going to it's not going to turn into ice on the surface of the moon. So it's basically going to be water molecules going to be bouncing all around the surface of the moon, and they can bounce around for a long time. But eventually, they're going to be bouncing around, and then they're going to all of a sudden bounce into a crater in one of these permanently shadowed regions. And as soon as it bounces in there, it slams into this super cold ice, and it just sticks. And this has been going on for billions of years. So it's built up a lot of ice in these craters. So there's a lot of ice, a lot of water in these craters. The problem is that it's in one of the coldest places in the solar system. There's probably a lot of dust in there, and moon dust is super abrasive, way more so than sandpaper. And how do you get energy down there, right? If it's so cold, if you were going to try and send any people down there, they'd freeze. If you send equipment down there, it would freeze. So it turns out that some of these places around here, and I don't know if there's a good example here, but there are, just like this is permanently shadowed, there are other places around some of the craters of the North and South Pole that are permanently in sunlight. So you've got a place that's permanently sunlight right next to a place that's permanently dark. So you can imagine having solar panels at the permanently lit places, always collecting energy, sending power down to the equipment that is mining the water, right? The other problem with the moon, though, is that you're at the base of the moon's gravity well, so they have to get out of the gravity. So this is just a schematic representation of one of those craters, Shackleton crater. It's this one's 21 kilometers in diameter, and you have this permanently shadowed region that's about 4 kilometers deep by almost 20 kilometers across. That could be a lot of water in it, right? It's just really difficult to get. So another place that you can get water from is asteroids, as I said. This is the asteroid Sirius. It's the largest asteroid in the main belt. It kind of looks like the Death Star from Star Wars. And I think when the first images came back of this, everyone was just blown away. I was blown away when it happened. It turns out that the current idea is that this bright spot you see here is actually a kind of a salt. It's not sodium chloride salt like that we eat, but it's a different kind of salt. And it comes up as a brine, as a salty water from the interior of Sirius. Sirius is basically bubbling up this material. And as the brine comes up, the water sublimates away. Sublimate, to remind you, means that it doesn't go through a liquid phase. It goes directly from a liquid to a gas phase. And it leaves behind these salts. But that means that there's an ocean inside Sirius that's actually bubbling up, this brine. And it turns out that our best estimates right now are suggesting that there is more water inside Sirius than there is on Earth. So if you could get to Sirius, there's lots and lots of water on Sirius, but Sirius is pretty far away. Yeah. Yeah, I'm terrible with numbers, remembering them. My memory is like 1,000 kilometers, but if you say 600 kilometers, we're within a factor of 2, and that's good enough for an astronomer. Yeah, okay. Yeah. So there's lots of water on Sirius, but Sirius is in the main belt of asteroids, right? Which is quite far away. So remember, asteroids and comets. Asteroids are icy dirt balls, comets are dirty ice balls. So there is water in these objects, and from that schematic movie I showed you of the main belt asteroids and near Earth objects, right? There were asteroids and comets that came into the inner solar system, and some of them come near Earth. That's why they're called near Earth objects. So maybe those could be good objects to try and get water from. So of all the different places you can get water from in our solar system to try and create this space economy, where is the best place to do it? Earth, difficult to get our Earth's gravity well. Moon, I explained there's lots of water there, but you've got the dust, you've got the cold, you've got the gravity well. Asteroids and comets, what about them? What is the best place? What is the most profitable way to get water and start our space economy? Well, just like in real estate, asteroids the same way. Not all asteroids are equal. It's all about location, location, location. So I told you about the near Earth objects already. They come close to the Earth, but it turns out that most of those are not actually that useful. They're hard to get to. And in fact, at any time, like right now, at this very instant, there is at least one 10-meter diameter asteroid. So think of the size of half of this room here, right? The place you're sitting, that's about a 10-meter diameter place. So there's an asteroid this size closer to us right now than the moon, right now, at this instant in time. The problem is that that asteroid is probably passing through our system so fast that is going to be hard to get to. It's not going to be easy to get to, and we don't know about it. So we need to be able to find an asteroid that we can find that's easy to get to and that has water in it. Okay, I lied. It's not just about location. It's also about delta V, delta V, delta V, right? Delta V is the amount of energy, the change in speed that it takes to get to an asteroid or comet. The more energy it takes to get there, and more importantly, the amount of more energy it takes to get back, the less profitable it's going to be, right? So you want to get asteroids and comets that are easy to get back from, so that you can basically not use up all your fuel bringing the material back. So it turns out that delta V is just, how much energy it takes. So delta V, we're all used to seeing rockets, and the rockets, the whole thing the rocket's doing is it's creating this delta V, this change in speed between the rocket sitting on the ground and the rocket in orbit. And so you need to add a lot of energy in order to get to these things. So it turns out that there's this low delta V zone of asteroids that we can get to. And that is sort of like, you can think of it as sort of like a donut or a torus around Earth's orbit. So if you've got Earth's going around the sun, counterclockwise at 1 astronomical unit of sun. And in this torus that's got a diameter of 20 million miles or so 10 million miles, from the Earth's orbit, anything that constantly orbits in that torus has a relatively low delta V. And we think that it's going to be suitable for being profitable for mining water from those kind of asteroids. Another thing you got to worry about is size, right? Not just location, delta V, it's also size. And it's a little bit like Goldilocks asteroid diameter, right? If you get an asteroid that's too small, say an asteroid that's just 5 meters or less in diameter, something less than half the size of this room, there's simply just not going to be enough water in it to make it profitable, right? You're not going to go try and, well, you might, if there was an oil pocket below your yard that was the size of this room, you'd probably try and extract it, right? But, it's not going to be worth it for Exxon to come in and do it, right? Exxon is just not, that's too small for us. So a less than 5 meter diameter asteroid, unless it happens to be some magical asteroid that's perfectly placed, is just not going to be profitable for us. On the other hand, an asteroid that's much, much bigger, say the size of the whole science center, right? That's too big for us. We just don't have any ideas at the moment of how we could handle it and actually extract the water from it. So the sort of the key, the sweet spot for us is somewhere in the range of 5 to 30 meters in diameter. Something about the size of a house, your typical house, okay, not Bill Gates' house, but a typical house, is sort of 20 meters in diameter, something the size of this room, but in all dimensions. We could sort of imagine doing something like that. So think of a potato or gigantic rock containing water that is about the size of your house. And the final thing, the fourth thing that you got to worry about for an asteroid is its taxonomy. Okay, taxonomy is just is mineralogy. What's it actually made out of? Is it an icy dirt ball? Is it a dirty ice ball? Or is it really just a completely dry piece of rock? Right? You don't want to go to an asteroid that turns out to be just completely dry, have no water in it. Right? So you got to worry about all these different things. So we put it all together. If you can find the right asteroid. And what we've done is I've said that early on that meteors are chunks of asteroids and comets that fell through our atmosphere. And when they hit the ground, they become meteorites. You can take a meteorite that's very fresh, that's not soaked up water from the Earth already. Take a very fresh meteorite. You can crush it up, put it in a test tube, put it on a Bunsen burner, and water comes out. Okay, so you can extract water from asteroids just by heating them up. And we've tested this even on a bigger scale at this place called White Sands Missile Range Solar Furnace in New Mexico that was used originally for atomic bomb testing. And this is a gigantic solar furnace, just like it says. And you can reach temperatures, I think it's something like 4,000 degrees at the focus here. So what we did is we took a rock, and when I say we, I'm taking, my whole field. I don't take credit for all these things. So anytime I said we, it wasn't me most of the time. We took this rock and it's a rock that is, all right, video's not playing. It's a rock that is it's an earth rock, but it's a good proxy for the kind of rocks that you find on asteroids, right? I mean, the Earth and asteroids are made out of the same things. In fact, a lot of asteroids are just like lava rocks on in Hawaii. So you can take one of these rocks, put it at the focus of that solar furnace, and you can see stuff boiling off of it. And in fact, if you could see this, you'd see chunks of rock flying off of this and steam coming out of it due to the solar furnace heating it up. So here's how we extract water from an asteroid, right? So here's the transastronomical concept. We've got these gigantic inflatable solar mirrors that collect sunlight, send the sunlight down these light pipes that goes down. It slams onto this asteroid that's contained in a bag. It blows the rock off the asteroid. The water comes out of the asteroid, goes into the bag, but eventually finds its way up into these cold traps, which are just like the craters on the surface and at the poles of the moon. And it's super cold in there, and all the water freezes in there. Once we've extracted all the water from the asteroid, we bring all the water back to the Earth-Moon system and sell it to somebody and make a lot of money. Now, you may think this is really crazy, right? You may think this is just as crazy as that artistic impression of mining an asteroid that had all the mining facility all over it. But in fact, 30 years ago, NASA actually flew a 14-meter diameter inflatable reflector in space. So this has been done by NASA 30 years ago. And this is real. This is not computer graphics. This is not Steven Spielberg. This is real. This is actually really done. And the technology has only improved since that time. And at TransAstra in Los Angeles, they are designing these inflatable mirrors and inflatable bags. And we have an entire laser system set up for testing whether or not our inflatable bags are producing a good enough quality mirror to generate the kind of temperatures that we need at the surface of the asteroid, right? Well, we're also, and NASA, as I designed, NASA didn't actually build this and test it in space, but NASA has actually designed a bagging system for an asteroid. That video is not playing either. Let me try one more time. Nope. Okay, so at TransAstra, we're also designing. This is real. Again, this is not fake. This is the only thing that's not real about this is that it's a time-lapse video. It doesn't go this fast. But this is all operating in gravity, so it'll work faster and better in space. But this is all inflatable bagging an asteroid system. Okay, this whole thing is an inflatable bag for an asteroid. We then have our fake asteroid that gets dropped into our bag, and then the bag closes. And this is all done by just manipulating the air pressure inside of those tubes. And then we have a robotic zipper that this is all self-controlled. We basically just tell the zipper to zip itself up, and it zips up the bag, and it creates a light-tight bag or an airtight bag. And then just using, again, the air pressure and some motor-driven straps, we can basically pull the asteroid in up to the focal point of the inflatable mirrors. So in order, the last step in the process, right, is we have to design all these things. But we also have to find the asteroids. The kind of small asteroids that we're talking about that are on these low delta V orbits are not the kind of asteroids that are being found by groups like Pan-STARRS and the Vera Rubin Observatory. Those observatories have the goal from the NASA's Planetary Defense Office of finding large asteroids that are dangerous for humanity. So our goal is to find asteroids that are smaller that can be mined. And so we've built already the system. We call it the Sutter system after the Sutter Mill, which started off the California Gold Rush, because we want to start off a water rush in space. So we call it Sutter, the Sutter Survey System. And it's currently working at the Sierra Remote Observatory in the Sierras. So we have this system. It's for those of you who want to know, this system here is 4 11-inch Celestron Raza telescopes, so they're wide-angle telescopes, and we're currently finding asteroids and tracking spacecraft and all sorts of cool things. And we're designing a spacecraft to look for asteroids in space because it'll be much better to find them in space, much easier to find small objects that we're actually interested in. We're talking about having sort of laser communication between our spacecraft and the Earth in order to have high data rates. And I won't get into all the details here, but we have ambitious plans for actually finding these asteroids. And then I hope how good this video is working. So We don't want to have our spacecraft in orbit around Earth because the Earth is very bright, the Earth is very hot. And we don't want to put our spacecraft where JWST is because JWST is in one location, always looking out. We want to have our spacecraft on something called distant retrograde orbits, which is a funny term. So here's the Earth here. It's a little blue dot, right here. And the moon is this other dot that's going around. It should continue. The little dot that's going around the Earth is the moon, of course, right? And these three things here represent our Sutter spacecraft. And the Sutter spacecraft, if you watch them, they look kind of like they're going around the Earth, right? But in fact, they're going around the sun. But they're on specific orbits that have been chosen to make it look like they're going around the Earth. And the thing is, if you were up here, up close, you'd see these little red dots. And the little red dots represent a synthetic population of these low delta V asteroids that are all in this torus that go around the Earth's orbit. So that the spacecraft that we've designed here and the orbits that they're on are flying sort of in formation through the population of asteroids that we actually want to identify so that we can mine them. So if you do the calculation, and this is something that I actually did, okay? If you do the actual calculation of how many asteroids there are in the right size range, in the right orbit range, of the right type containing water, it turns out that there's about 100,000 tons of water available in that torus, okay? And that 100,000 tons of water is worth about $1 trillion, okay? So here's me. I've talked to you about the peril of asteroids and what we're trying to do about not perishing. I've talked to you about the profit of near-Earth asteroids. And this is my question that I have to ask, right? To perish or profit by near-Earth asteroids? Personally, I want the profit. I want to be the first billionaire astronomer. And someday I hope you'll read about me. You'll see pictures of me dining with Elon Musk or something. The end. Thank you very much. Does anybody other than David have a question?
Yeah, let's turn the lights up and
Not that you can't ask a question, David, just
I know that
encouraging other people.
somebody might have dropped one in the chat window here. No, somebody said memories of Clyde Tombaugh. I don't know what that was about.
Obviously, it's a story. I think one of the key questions I have what is the obviously working with fan system to get water? What is the price to get in that kind of water here? Is it really worth the amount of obviously spacecraft to go extract of that? Obviously, it's going to be a lot of work, but obviously, the price of the ship. What do you expect?
Yeah, so we get that question a lot, and I think of course it's the question to ask. But you like think back to before there were cars, before there were gas stations everywhere. And if you'd said, 20 years before all of that sort of started building up, you said, well, isn't it going to cost a lot of money to build all these gas stations? And who's going to buy cars when there's no gas stations, right? And so there's this sort of a spiraling development of an economy that has to occur. And that's what we're trying to do. And is it difficult? When cars first came out, my understanding, and I'm no historian, but my understanding is that electric cars were actually more prevalent than gas-powered cars at the beginning, right? And there was this sort of a fight between them to see which was going to win out, and the gas-powered cars went out for 100 years. And so, I like to think that that's sort of the stage we're at right now with this space economy. What is the actual material that is going to be the most profitable in the beginning to actually jumpstart the space economy? And you said, is it worth it to bring the material back here? Well, for one thing, we're not bringing the water back to Earth. We're bringing the water back to high Earth orbit, and that's constantly changing, right? SpaceX and other companies, what is it called? I forget the name of the company. I just read it. They're 3D printing launch vehicles now. I forget.
Well, Astra's doing it. And,
Okay, it doesn't matter. But the whole cost of launching things into space is going down. So that means the cost of launching water into space is going down. And that obviously is going to affect the price point for water. But the other point is that it also decreases the launching our spacecraft. And the cost of launching our spacecraft is one of the major costs for us as well. So that brings down our price point, right? So it's a capitalistic, competitive market, and I think it's kind of interesting. And if you don't try, nothing ever happens, right?
Rob, we have a couple of questions on the internet from the cloud. Will mining asteroids change the direction of them and perhaps set them on a collision course to Earth?
So changing the direction and course of things is hard. That's one of the things we're trying to do with deflecting asteroids that might be on a path to Earth. So and also we're not really changing the center of mass of things. There's a whole bunch of things that we can do. So for one thing, we're talking about really small asteroids. And remember, the mass of the Earth increases every year by 100,000 tons because of asteroid impacts. The mass of the Earth increases by 100,000 tons a year. The Earth gets hit all the time by meteors, right? And we're talking about a 20, 30 meter diameter asteroid that we're trying to mine. If we converted that entire thing into dust and it hit the Earth wouldn't notice it at all, right? So I guess what I'm trying to say is that we aren't going to be changing the path of the asteroid, and anything that we do left, any debris that we do leave there will be nothing more than a meteor shower if it ever does come into contact with the Earth.
Got it. The other question here, I'm actually going to rephrase the second question because the anonymous asker missed the point that the water you're mining is not to bring back to Earth because we need more water in California, but it's because you want the water collected in some Earth orbit where it could be utilized in space. We're trying to reduce the cost of water in space. But part of the question is, what else can you mine that would be profitable? What other thoughts have you had?
So I don't think about these. I'm an astronomer, not an entrepreneur. And so I don't think about these things. I know that asteroids contain, I think some asteroids can contain a lot of valuable rare earth metals. But my understanding is that those rare earth metals are not like on the Earth. On the Earth, you go and you find veins of gold and veins of silver and platinum and things tend to be together. But my understanding is that if you're on an asteroid, there is gold and there is silver and there's platinum on these asteroids, but it's sort of evenly distributed, and processing it is much more difficult. But again, I'm not a planetary geologist. I don't know the details. That's my understanding, that it's actually really hard to do these things, and people haven't really put a lot of thought into how they would go about mining these things.
No one's looking for the golden asteroid.
Oh, not that I'm aware of. Not that I'm aware.
Well, that also answered our third question. Anybody else in the room?
By the way, and yes, our idea is not to bring the water back to Earth, but you could sort of imagine, we actually did a price point and we looked for, how much people will actually spend for water, and people spend $3,000 for a liter of water if it comes from some crazy place.
Oh, the novelty water.
The novelty water.
Yes.
And so, if we can find somebody who's willing to pay us $10,000 for a liter of water because it came from an asteroid, we'll sell it to them.
Hi. Yeah, I know you mentioned The Expanse, and in that show, they would spin asteroids to make them spin faster and then build a space station in the interior of the asteroid with the centripetal acceleration as gravity, basically. So my question is, I know many asteroids are described as kind of just a loose collection of rubble, but do you think that there are asteroids where that could be feasible to do that?
So yeah, my understanding is that basically all asteroids are rubble. Even big ones are rubble. When they measure the density of asteroids, it turns out not to be like the density of Earth. sort of 5 tons per cubic meter. Turns out to be typically 1 or 2 or 3, which means there has to be a lot of porosity inside of it. And the idea is that most asteroids have suffered multiple collisions in their history, and they've sort of been broken apart and then reaccumulated. And it's just that the bigger ones have got more sort of self-gravity, that they've been able to become more spherical. And it's only the smallest ones that don't have enough self-gravity to become spherical. So, I don't know, again, I'm not an engineer to know whether or not you can actually spin these things up. I would think that if you spun them up enough to create gravity inside, you'd probably throw off all the material. But if you could find a way to hold it all together, right? And then, expand it and let it sort of fill the exterior, and then go interior to that, you could use that material as a regolith, as a radiation shield to protect the people that are inside. But again, I'm not an engineer, and I have not thought about these things deeply.
Nate? Give you the mic.
Was the telescope that's in Chile that's about to come online in a couple of years, is that also known as the LSST?
It's the telescope formerly known as the LSST.
Oh, formerly known, so
Yeah.
it's the same one.
So it's now called the Vera Rubin Observatory, and they're running what they call the Legacy Survey of Space and Time, which also happens to have the acronym the initialism LSST. So instead of being the LSST telescope, it's now the VRO that's running the LSST.
Okay.
Anyone else? Or Steve.
Thank you. It seems that in order for asteroid mining to develop into an economically viable enterprise, there has to also be developing simultaneously a way to get the stuff. I would call it an inner solar system transport infrastructure. And what time scale? I mean, I'm sure that will eventually be developed, because that'll be needed for scientific exploration and development of Mars and other places in the inner solar system. What time scale are we talking about? Can you imagine?
I think, as always, it's all about how much money people want to put into it. NASA is developing something called I think it's called the Lunar Gateway, which is supposed to be some sort of almost like a way station between the Earth and the Moon, closer to the Moon than the Earth. And it would fulfill a lot of these things you're talking about. It would be sort of a place that's at not down in the gravity well of the Moon, not down in the gravity well of the Earth. It's sort of in between. So you could use it as sort of a way station. So for instance, TransAstra could bring water there. It could be like a fueling station for other companies, groups that want to go there to pick up the water. NASA is currently working a lot on technologies to mine water from the lunar poles. They're funding a lot of research into landing landers there and exploring those areas. And then you've got other commercial companies that are developing things like space hotels, inflatable space hotels, and other things. And if there's inflatable space hotels, they're going to need water for people, and it'd be cheaper maybe. Well, we'd like to think that we can make it cheaper for them to supply water from TransAstra than to bring up water from Earth to the space hotels. So you're right, it has to be this sort of bootstrapped economy, as I was talking about earlier with the gas. But you got to start somewhere, and you got to have some people with vision who are willing to just move forward and pray that it will be there. I'll use a football analogy, right? If you haven't played football before, I don't know if you know this, but when the offensive line is trying to clear a path through the defensive line, and when the quarterback actually hands off to the running back, and the running back is running towards the offensive line, but when the handoff takes place, there is no hole where the running back is supposed to run through. That hole is going to open up because of the timing of everything. It's all split-second timing, right? So the running back and the quarterback have faith that the offensive linemen, I was offensive lineman, are going to open up that hole. And so you have to have faith that the market is going to be created as you create little bits and pieces of it. Everybody else is doing their bit, and everything will build up together.
Steve, I think that infrastructure will be in place immediately after the completion of California's high-speed rail.
Yeah.
Anybody else?
Yeah, just one last question. So Let me remember for a second. So, obviously, as you said, well, you're big up in this industry, and specifically in this capture and asteroid mining. Did you say interest has really been waning in this? I mean, surprising given the type of profits that we could looking at with this, just in this around Earth, humongous, I mean, trillions of dollars, right? So would you say interest has been waning? Because I've never seen very much talk about this in media or interest even with other companies. So would you say interest has been waning, or is it growing bigger than ever and just behind the scenes,
That's a hard question for me to answer because I think I'm so involved and I read everything about it. I don't really necessarily have a good sense of what the rest of the people are thinking about. Certainly the Earth has got lots of problems. And I think it's arguable that the other problems are maybe more important to deal with. But I think that if you're not also thinking about heading into space and exploration of space, then you're sort of giving up on things too. So I think that going into space can create hope, and it can create an option to help us move forward. There's also ideas. One of my colleagues just published an article about using an asteroid as an anchor to hold a sun shield in place at the Lagrangian point between the Earth and the sun. And so you can't just put a big solar sail there because it'll just blow away by the sun. But if you have an asteroid there, you can actually anchor it there. And so an asteroid might be able to be used as an anchor for a solar sail, right? And then there's another idea that there's a group that I'm sort of working with called Astronomical. And the idea there is to use maybe asteroid dust at that location to block sunlight, right? So these are two ideas using asteroids that have got to do with actually solving or reducing the effect of climate change, right? So if you don't think these big things, you may not have big solutions. David had a question.
I have several. But again, I'm driving you back to your hotel, so I can.
Oh, it's
Hold
true,
on.
that's true.
You got to talk in the
Oh,
microphone,
okay.
or else nobody online hears you.
Actually, that may be a blessing.
Well, that's true. Forget it.
How about one question for David and then
Only one?
and you got me in the car all the way back.
I know, but then other people can't hear your
Oh,
answers to
yeah,
the
that's true.
question. So,
Okay.
first thing I want to comment on is that both my wife and Gerald corrected me about the size of Ceres. You were right and I was wrong. Your bad numbers are better than my good numbers. But congratulations. Rebecca's looked it up and you said 950 kilometers. And then Gerald, being Gerald, wrote out in three dimensions. Gerald, what is your number?
965 by 961 by 891 kilometers.
Only three significant digits. Gerald is being more sloppy than he usually is. Okay, I had a question. My big question, I have a lot, is your calculation about the amount of water. How did you do that? And what is your assumption? Okay, this also gets into the taxonomy question because we have all these asteroids, and I'm assuming that you're not assuming that they're all the same.
Yeah, it's complicated, and that's actually how I got involved with Transasteroid, because I was at a conference about 10 years ago, and the Transasteroid CEO, his name is Joel Searle. He's a aeronautical engineer, PhD from Caltech.
What's his name?
Joel Searle.
Yeah.
He and I met at a conference, and he said, "Well, how many asteroids are there we can mine water from?" I said, "I don't know. I have to do that calculation," and it took me a couple of years. But so what we do, and I'll try and give a very, very brief overview of it, is we've developed models of the near Earth object population. So where the asteroids are, how many there are, and as a function of their location in the solar system. And there are also other models that talk about the taxonomic model, the modeling. And what I did is I combined the taxonomic modeling, the mineralogical modeling, with the orbit distribution modeling to estimate how many there are of a particular type in near Earth object space. And then I worked out how many of those are in that torus near the Earth's orbit. And then I said, I asked what fraction of the ones that are in the torus around Earth's orbit are of the type of the taxonomy that contains, say, 15% water by mass.
Okay.
And then I assumed that given that fraction that contain the 15% water by mass, and then you take the 15% of those asteroids, that's where you get the 100,000 tons from.
I see. Do we understand the taxonomy and the variation of the taxonomy of near-Earth asteroids to that level of accuracy that we can actually say that the 15% number I find surprising?
So I think for an individual asteroid that's not been studied deeply, we know little about it other than statistical treatments, but we have lots of samples of asteroids on the Earth in the form of meteorites,
Yes,
and we can measure the water content in the meteorites.
we have
And-
Peril in our house, by the way. but
Oh, do you?
that-
Okay.
Yes,
And those those meteorites, have broken into different types. And there are classes of those meteorites that contain 15% water by mass. But even then, when you talk about that, there's a huge selection effect that happens with meteorites, because the stuff that makes it to the surface of the Earth is going to be the hardest bits that come in. It's not going to be the softest bits. And there's this famous meteor that happened over Canada called Tagish Lake. And the Tagish Lake meteor was very bright, and it broke up and it blew a whole bunch of stuff all over the tundra. And it was dark, it was coal, and I'm told that it smelled like coal. It was really organic, not organic, but it it was coal-like, and it was very crumbly. And so when they picked it up, they actually had to sometimes, like, they would use a chainsaw to dig a hole around it and actually lift it up and put it into a freezer, because if they let it freeze, or if they let it thaw, it would actually just turn into muck.
ooh,
Right? So there's so much water in those things that they don't last very long. So if those things fall on the surface of the Earth, they don't last very long, and we wouldn't even have them in our records, right? So it's really difficult to get a really good estimate of how much water is in there. And now we know that, with this asteroid sample coming back from Bennu used with OSIRIS-REx, there's evidence that Bennu contains water. Hayabusa did not Hayabusa 2, I think it was, brought back. Was it Hayabusa 2 or Hayabusa? I forget. The Japanese missions brought back samples that also contain water, or they did studies of the asteroid that they went to that show that it has water. So these asteroids do have water on
what
them.
were the percentages on the Hayabusa mission, and what do you know?
I don't remember.
That's okay.
Yeah, right. Yeah, in general, there's these S-type asteroids that are thought to not contain much water, and there's the C-type asteroids that contain more water. But even within the C-types, there's different subtypes that contain more and less, right? So
I assume we're saying that there are very large error bars in our understanding of the composition of the potential NEOs. Is that correct?
yes, and so you would have to before we went to an asteroid to try and extract water from it, we'd try and do as much as we can beforehand remotely to increase the probability that's the kind of asteroid that contains water. But again, I sort of go back to the analogy of the oil industry, right? The oil industry, and I actually have some slides that come after this. The oil industry spends $1 billion to build a drilling platform, an ocean drilling platform, and they drill, I don't know, 50 wells before they find one that's profitable, right? And I think that that's sort of the idea that we have to think about if you're starting a new business in space as well, right? You can't. Oh, you certainly hope that you're going to go to your first asteroid and you're just going to find water. But I don't think that when they started drilling for oil that they necessarily hit oil every single time they drilled as well.
They
So
certainly do. Do you have any idea what the capitalization is of Transaster? That's a financial question.
it's a private company, and I'm not privy to that information.
Okay, okay. I'm going to stop for the moment.
All right, well, I don't see any other questions from there's another question here. Not a question, but a compliment. Amazing presentation and very informative.
Oh, thank you.
So, there we go. All right, everyone. Thank you so much for attending tonight, both here and online. We had a great turnout, and enjoy the rest of your weekend. And
Don't forget next month's speaker. Oh, yes. Once again, forgive me for being repetitive, but people always ask me, what is the secret to education? And I always say repetition, repetition, repetition. So next month's speaker will be Dr. Sarah Moran, again from the Lunar and Planetary Lab, which is Rob's old alma mater, talking about observing planets both inside and outside the solar system with James Webb Space Telescope. And practically every week, James Webb is making these fantastic discoveries. And so I urge you to come because this is, I mean, we're really on the edge of some amazing, amazing discoveries. We may discover Earth-like planets within a few years. And with that, I think I'm done. Anything else you want to say, Rich? Okay.
All right, everyone have a good weekend and we'll see you next time.